Tonight on The Sleepy Scientist, we're drifting gently through the vast cosmic ocean, where stars dance in pairs across the infinite darkness and worlds orbit not one sun, but two. In the quiet space of our imagination, we find ourselves floating toward a discovery that once lived only in the realm of science. Fiction, a planet bathed in the gentle light of twin stars. A world where binary sunsets paint the sky in colors we can barely comprehend. Here. In this moment of peaceful contemplation, we turn our attention to Kepler-16b, a world that exists 145 light-years from our own blue marble. Spinning silently in the constellation Cygnus, gently we discover this distant planet offers us a window into the extraordinary diversity of planetary systems that populate our galaxy, each one a testament to the creative forces of cosmic evolution. The story of Kepler-16b begins not with drama or excitement, but with the patient, methodical work of scientists who spend their nights listening to the whispers of distant stars. Like whispers in the night, the faint dimmings of starlight carry messages across the vast emptiness of space, telling us of worlds that block the light of their parent stars as they complete their eternal orbits. In the quiet space of scientific discovery, we learn that this particular world represents something unprecedented in our understanding of planetary formation and evolution. Unlike the planets of our own solar system, which orbit a single star in relatively simple, predictable paths, Kepler-16b follows a complex dance around two stars that are themselves locked in their own gravitational waltz. The two stars of the Kepler-16 system, designated Kepler-16a and Kepler-16b, circle each other every 41 days in a cosmic choreography that has continued for billions of years. The larger of the two, Kepler-16a, is a K-type star, smaller and cooler than our own Sun, glowing with a gentle orange light that would bathe any nearby world in hues reminiscent of a perpetual autumn sunset. Its companion, Kepler-16b, is even smaller, a red dwarf star that adds its own subtle contribution to the binary systems. Total LUMINOSITY. Together, these stellar companions create what astronomers call a circumbinary system, a gravitational environment where planets can form and survive despite the complex tidal forces and gravitational perturbations that arise from having to massive objects at the system's center. Gently, we discover that such systems are far more common than we once believed, suggesting that the universe is filled with worlds experiencing the unique phenomena of binary starlight. The discovery of Kepler-16b in 2011 marked a pivotal moment in exoplanet science, not because it was the first planet found orbiting a binary star system. That honor belongs to PSRB 1620-26b, a world orbiting a pulsar white dwarf binary, but because it was the first such world detected using the transit method, where we observe the planet passing in front of its host stars from our vantage point on Earth. This method of detection requires extraordinary precision and patience. Imagine trying to detect the shadow of a butterfly as it passes in front of a pair of lighthouse beams from hundreds of miles away. The dimming of starlight caused by Kepler-16b's transit is similarly subtle, requiring the sensitive instruments of the Kepler Space Telescope to detect the minute changes in brightness that reveal the planet's presence. Like whispers in the night, these tiny fluctuations in stellar brightness carry profound implications for our understanding of planetary formation. The very existence of Kepler-16b challenges some of our earlier assumptions about how planets can form and maintain stable orbits in the gravitationally complex environment of a binary star system. The planet itself is roughly the size of Saturn, with a mass approximately 105 times that of Earth. It's what astronomers classify as a gas giant, a world composed primarily of hydrogen and helium, with no solid surface upon which we might imagine standing to witness the spectacular sight of twin sunrises and sunsets. Yet even though we cannot walk upon its surface, Kepler-16b offers us invaluable insights into the processes that shape planetary systems throughout our galaxy. Its orbit around the binary pair takes approximately 229 Earth days to complete, carrying it along a path that remains remarkably stable. Despite the gravitational complexity of its environment, This stability speaks to the delicate balance of forces that allows such worlds to exist, a cosmic harmony that has persisted for the billions of years since the planet's formation. The temperature on Kepler-16b is estimated to range from -73 to -101 degrees Celsius, 100 to -150 degrees Fahrenheit, making it far too cold to support liquid water on its surface if indeed it had a surface. This frigid environment places the planet well outside what we traditionally consider the habitable zone, the region around a star where liquid water could exist on a planetary surface. Yet even in its cold exile, Kepler-16b serves as a crucial piece in our growing understanding of planetary diversity. In the quiet space of scientific analysis, we begin to appreciate how this world's very existence expands our definition of what is possible. In the realm of planetary formation and evolution, the story of Kepler-16b is also intimately connected to the broader narrative of the Kepler Space Telescope mission, one of the most successful planet-hunting endeavors in the history of astronomy. Launched in 2009, Kepler spent nearly a decade staring at a small patch of sky in the constellation Cygnus, monitoring the brightness of over 150,000 stars with unprecedented precision. Gently, we discover that this patient vigil revolutionized our understanding of planetary systems, revealing thousands of new worlds, and demonstrating that planets are not rare cosmic accidents, but rather common features of stellar systems throughout our galaxy. Among these discoveries, Kepler-16b stands out not just for its unique binary configuration, but for what it tells us about the remarkable diversity of planetary environments that exist beyond our solar system. The discovery also carries profound implications for our search for life in the universe. While Kepler-16b itself is unlikely to harbor life as we know it, its existence suggests that habitable worlds might exist in binary star systems that make up a significant fraction of all stellar systems in our galaxy. This possibility effectively doubles the number of potentially habitable environments we might explore in our ongoing search for life beyond Earth. Like whispers in the night, the data from Kepler-16b continues to inform our understanding of planetary formation models, helping astronomers refine their theories about how planets can emerge from the swirling disks of gas and dust that surround young binary stars. These models, in turn, help us predict where else we might find similar worlds and what conditions might be necessary for the formation of potentially habitable planets in binary systems. The visual experience of living on or near Kepler-16b would be unlike anything we know from our own solar system. Imagine, if you will, the sight of two suns of different colors and sizes moving across an alien sky, sometimes close together, sometimes separated by significant angular distances, creating complex patterns of light and shadow that would change not just throughout each day, but throughout the planet's year as its orbital position relative to the binary pair shifts. During some parts of the planet's orbit, both stars would be visible simultaneously, creating a landscape illuminated by the combined light of the orange K star and its red dwarf companion. At other times, one star might eclipse the other from the planet's perspective, creating temporary periods of dimmed illumination that would add yet another layer of complexity to the world's light cycles. In the quiet space of our contemplation, we can imagine how such conditions might influence any potential atmospheric dynamics on the planet. The varying intensity and spectral composition of the light reaching Kepler-16b throughout its orbit would create heating patterns unlike anything experienced by planets in single-star systems, potentially driving unique atmospheric circulation patterns and weather systems. The gravitational environment of Kepler-16b is equally fascinating from a physics perspective. The planet experiences not just the gravitational pull of the two stars, but also the complex gravitational field created by their orbital motion around their common center of mass. This creates what astronomers call gravitational perturbations, subtle variations in the planet's orbital path that would be impossible in a single star system. These perturbations, while small, have measurable effects on the planet's orbit over long time periods. They create a kind of orbital precession, where the planet's elliptical orbit gradually rotates in space, and they introduce subtle variations in the orbital period. that can be detected by careful analysis of the transit timing variations observed by space telescopes. Gently, we discover that these gravitational effects serve as additional confirmation of the planet's existence and help astronomers precisely determine its orbital characteristics and mass. They also provide insights into the long-term stability of the orbit, helping us understand whether such worlds can maintain stable orbits over the billions of years, necessary for complex processes like atmospheric evolution or, potentially, the development of life. The formation history of Kepler-16b remains an active area of research and debate among planetary scientists. Traditional models of planetary formation assume a single central star, around which a protoplanetary disk of gas and dust gradually coalesces into planets. In a binary system, this process becomes significantly more complex, as the gravitational influence of both stars affects the distribution and dynamics of material in the protoplanetary disk. Some models suggest that planets like Kepler-16b might form at greater distances from the binary pair, where gravitational perturbations are less severe, and then migrate inward to their current orbits over millions of years. Other models propose that they could form in situ, growing from material that remains in stable orbits despite the complex gravitational environment. Like whispers in the night, the clues to this formation history are embedded in the planet's current characteristics: its mass, orbital period, orbital eccentricity, and the composition of its atmosphere, if we could measure it in detail. Each of these properties carries information about the conditions that existed during the planet's formation and the processes that shaped its evolution. Over cosmic time, the study of Kepler-16b also contributes to our broader understanding of stellar evolution in binary systems. The two stars of the Kepler-16 system are at different stages of their evolutionary development, with the primary star Kepler-16a more massive and therefore evolving more quickly than its red dwarf companion. Over the course of billions of years, this system will undergo changes that will dramatically affect any planets orbiting the binary pair. Eventually, Kepler-16a will exhaust the hydrogen fuel in its core and begin to evolve into a red giant star, expanding too many times its current size and dramatically increasing in luminosity. This stellar evolution will fundamentally alter the radiation environment of the system, potentially affecting any atmospheres that planets like Kepler-16b might possess. In the quiet space of cosmic time, these changes unfold over timescales that dwarf human civilization, yet they represent crucial phases in the life cycles of planetary systems. Understanding how planets survive or fail to survive these stellar evolutionary changes provides important context for our studies of planetary atmospheres and the long-term habitability of worlds. In binary systems, the discovery of Kepler-16b has also sparked renewed interest in the possibility of moons orbiting planets in binary star systems. While no moons have yet been detected around this particular world, the gravitational dynamics of binary systems could potentially support large, stable satellites that might themselves be habitable, despite their host planet's location outside the traditional habitable zone. Such exomoons, if they exist, would experience an even more complex gravitational environment than their host planet, with tidal forces from both the planet and the binary star system, potentially driving internal heating that could maintain liquid water beneath ice-covered surfaces, similar to some of the moons. In our own solar system, gently, we discover that each new piece of information about Kepler-16b and similar worlds expands our appreciation for the incredible diversity of planetary environments that exist throughout our galaxy. From the scorching surfaces of planets orbiting close to their stars to the frozen realms of worlds like Kepler-16b, the universe presents us with an almost unlimited variety of conditions under which matter organizes itself into planetary systems. This diversity challenges us to think beyond the familiar patterns of our own solar system and to consider the full range of possibilities for planetary formation, evolution, and potentially even the development of life. Each new discovery adds another piece to the grand puzzle of cosmic evolution, helping us understand not just how our own Earth came to be, but how countless other worlds throughout the universe have followed their own unique paths of development. we begin to appreciate that Kepler-16b represents more than just an interesting astronomical curiosity. It serves as a bridge between the familiar single-star planetary systems we know from our own cosmic neighborhood and the vast majority of stellar systems in our galaxy, many of which consist of binary or multiple star configurations. The implications of this realization are profound for our ongoing search for habitable worlds, and potentially even life itself. If planets can form and maintain stable orbits in binary systems, as Kepler-16b clearly demonstrates, then the number of potential sites for habitability in our galaxy is effectively doubled, opening up vast new territories for future exploration and study. Like whispers in the night, the data from this distant world continues to inform our understanding of planetary science, stellar dynamics, and the conditions necessary for the formation and evolution of planetary systems. Each measurement, each observation, each theoretical model inspired by Kepler-16b contributes to our growing library of knowledge about the cosmos and our place within it. The story of Kepler-16b is ultimately a story about the power of patient observation and careful analysis to reveal the hidden wonders of the universe. It reminds us that even in an age of spectacular space missions and dramatic discoveries, some of the most profound insights come from the quiet, methodical work of scientists who spend years analyzing subtle patterns in data, listening for the faint signals that reveal the presence of distant worlds. In the quiet space of scientific discovery, we find that the universe is far stranger, far more diverse, and far more wonderful than we ever imagined. Kepler-16b stands as a testament to this cosmic creativity, a world that challenges our assumptions and expands our understanding of what is possible. In the vast expanse of space and time, let's drift into a deeper exploration of the mission that made this discovery possible, the remarkable Kepler Space Telescope, and the gentle precision with which it revealed the secrets of distant worlds. In the next chapter of our cosmic journey, we'll explore how patient observation and technological innovation combined to open our eyes to the existence of planets, orbiting binary stars, forever changing our understanding of planetary systems throughout the galaxy. In the quiet space of March 2009, a Delta II rocket lifted gently from Cape Canaveral, carrying with it humanity's most sensitive planet-hunting instrument, the Kepler Space Telescope. This was not a dramatic launch filled with thunder and fury, but rather a methodical ascent into the cosmos, carrying with it the hopes and dreams of astronomers who had spent decades preparing for this moment of quiet revelation. The Kepler mission represented a fundamental shift in our approach to discovering exoplanets. Before Kepler, most planet discoveries relied on detecting the gravitational wobble that planets induce in their host stars, a method that worked well for large planets orbiting close to their stars, but which struggled to find smaller, more Earth-like worlds in longer period orbits. Kepler's approach was different, almost meditative in its simplicity. Rather than looking for the gravitational effects of planets on their stars, it would watch for the tiny dimmings of starlight that occur when a planet passes in front of its host star as seen from Earth. This method, called transit photometry, requires extraordinary patience and precision, qualities that defined the Kepler mission from its inception. Gently, we discover that the concept behind transit detection is elegantly simple, yet challenging to implement. When a planet crosses in front of its star during its orbit, it blocks a tiny fraction of the star's light, creating a brief, periodic dimming that can be measured by sensitive instruments. For an Earth-sized planet passing in front of a Sun-like star, this dimming amounts to less than 0.1%, a change so subtle that it requires space-based observations to detect reliably. The Kepler spacecraft was designed as a photometer of unprecedented sensitivity, capable of measuring the brightness of stars with a precision that would have seemed impossible just decades earlier. From its orbit around the Sun, trailing behind Earth, Kepler stared continuously at a single field of view in the constellation Cygnus, monitoring the brightness of over 150,000 stars simultaneously. Like whispers in the night, the tiny variations in stellar brightness were recorded and transmitted back to Earth, where teams of scientists would spend years analyzing the data for signs of transiting planets. The choice of the Cygnus field was deliberate and strategic. This region of the sky is rich in stars similar to our Sun, providing a large sample of potential planetary systems to study. More importantly, Cygnus is positioned such that Kepler could observe it continuously, without interference from the Sun or Earth, allowing for the uninterrupted monitoring necessary to detect the periodic transits of planets, with orbital periods measured in months or years. In the quiet space of its solar orbit, Kepler began its patient vigil, collecting photometric data with a cadence that would make metronomes envious. Every 29.4 minutes, the spacecraft would record the brightness of each target star, building up a database of measurements that would eventually span nearly a decade of continuous observation. The detection of planets using the transit method requires more than just observing a single dimming event. True planetary transits must be periodic, occurring at regular intervals as the planet completes its orbit around the host star. They must also have specific characteristics of particular shape and duration that matches theoretical predictions for planetary transits, distinguishing them from other phenomena that might cause similar brightness variations. For binary star systems like Kepler-16, the analysis becomes even more complex. The two stars orbit around their common center of mass, causing periodic eclipses as one star passes in front of the other. These stellar eclipses are much deeper than planetary transits, often dimming the combined light of the system by several %, and they occur with a regularity determined by the orbital period of the binary stars themselves. Gently, we discover that detecting a planet in such a system requires disentangling the deep regular eclipses of the binary stars from the much shallower, less frequent dimming events caused by a planet transiting across the face of one or both stars. This analysis demands sophisticated computer algorithms and careful statistical analysis to distinguish genuine planetary signals from instrumental noise and stellar variability. The Kepler team developed innovative techniques for analyzing these complex light curves, using methods borrowed from signal processing and time series analysis to identify periodic patterns buried in noise. They created automated algorithms that could scan through thousands of light curves simultaneously, flagging potential planetary candidates for further analysis by human experts. The discovery process for Kepler-16b began with the automated detection of unusual transit-like events in the light curve of the Kepler-16 binary system. The initial signals were puzzling. They showed dimming events that occurred at irregular intervals and had unusual shapes that didn't match the expected profile of a planet transiting a single star. Further analysis revealed the true nature of these signals. They were caused by a planet that was sometimes transiting the primary star Kepler-16a, sometimes transiting the secondary star Kepler-16b, and sometimes transiting both stars simultaneously. The irregular timing of these events reflected the complex orbital dynamics of a planet moving around a binary star system, where the changing positions of the two stars create a constantly shifting gravitational field. Like whispers in the night, these subtle variations in transit timing and depth carried detailed information about the orbital characteristics of both the planet and the binary star system. By carefully analyzing the pattern of transits over multiple orbital periods, astronomers could determine not only the size and orbital period of the planet, but also the masses and orbital characteristics of both stars in the binary system. The analysis of Kepler-16b's transits required months of careful work by teams of astronomers and computer scientists. They had to account for the gravitational effects of both stars on the planet's orbit, model the complex geometry of a three-body system where all objects are in motion, and disentangle the subtle variations in transit characteristics caused by the changing relative positions of the planet and stars. This work was made possible by the extraordinary stability and precision of the Kepler spacecraft. Over its operational lifetime, Kepler maintained photometric precision at the parts per million level, allowing astronomers to detect variations in stellar brightness that would have been completely invisible to ground-based telescopes or earlier space missions. In the quiet space of data analysis, patterns emerged that told the story of a world unlike any in our solar system. The transits of Kepler-16b showed that this planet maintains a remarkably stable orbit, despite the complex gravitational environment of its binary host system. The orbital period of 229 days places it well outside the chaotic zone, where gravitational perturbations from the binary stars would destabilize planetary orbits. The Kepler mission's approach to planet detection was inherently statistical in nature, because the transit method only works when a planet's orbital plane is aligned nearly edge-on as seen from Earth, a geometric coincidence. That occurs for only a small fraction of planetary systems. The telescope had to monitor thousands of stars simultaneously to detect significant numbers of transiting planets. This statistical approach revealed fundamental insights about the frequency and characteristics of planetary systems throughout our galaxy. By observing such a large sample of stars over an extended period, Kepler could determine not just the properties of individual planets, but also the statistical distributions of planetary sizes, orbital periods, and system architectures that characterize the galaxy as a whole. The discovery of Kepler-16b was particularly significant because it demonstrated that circumbinary planets' worlds orbiting binary star systems are not rare cosmic curiosities, but rather a common type of planetary system. This realization effectively doubled the number of potential sites for planet formation in our galaxy, since roughly half of all stars exist in binary or multiple star systems. Gently, we discover that the Kepler mission transformed our understanding of planetary systems through the power of sustained, precise observation. Unlike missions that rely on brief encounters or targeted observations of specific objects, Kepler's strength lay in its ability to monitor the same stars continuously for years, building up datasets of unprecedented depth and duration. This continuous monitoring was essential for discovering planets like Kepler-16b, whose orbital period of 229 days meant that only a few complete transits occurred during the primary Kepler mission. Ground-based follow-up observations would have been virtually impossible, given the tiny amplitude of the transit signals and the complex interference patterns created by Earth's atmosphere. The spacecraft's design reflected the mission's commitment to photometric precision. Every aspect of the instrument was optimized to minimize noise and maximize stability. The telescope was designed to avoid pointing at the Sun, Earth, or Moon, which could introduce thermal variations that might affect the sensitive CCD detectors. The spacecraft maintained a constant orientation relative to the stars, minimizing the effects of thermal cycling and mechanical flexure. Even the choice of the spacecraft's orbit was carefully considered to support the mission's scientific goals. By placing Kepler in an Earth-trailing heliocentric orbit, mission designers ensured that the spacecraft could observe its target field continuously, without interruption from Earth's shadow or the need for periodic orbital adjustments. Like whispers in the night, the data from Kepler accumulated slowly but steadily, with each observation adding to a growing database that would eventually transform our understanding of planetary systems. The mission collected over 600 gigabytes of scientific data during its primary mission, with each data point representing a measurement of stellar brightness, accurate to a few parts per million. The processing and analysis of this data required new computational techniques and theoretical frameworks. Traditional methods for analyzing stellar photometry were inadequate for handling the volume and precision of Kepler data, leading to the development of new algorithms for transit detection, false positive identification, and systematic error correction. The Kepler team pioneered the use of automated transit detection algorithms that could process light curves from thousands of stars simultaneously, identifying periodic dimming events that might indicate the presence of transiting planets. These algorithms had to be sophisticated enough to distinguish genuine planetary transits from various types of astrophysical false positives, including background eclipsing binaries, stellar variability, and instrumental artifacts. In the quiet space of scientific analysis, each potential planet detection underwent rigorous validation. The Kepler team developed a comprehensive framework for assessing the probability that a given signal represented a genuine planet rather than a false positive. This framework included detailed modeling of instrumental systematics, statistical analysis of signal characteristics, and extensive ground-based follow-up observations. For Kepler-16b, this validation process was particularly complex due to the unusual nature of the transit signals. The irregular timing and varying depth of the transits initially raised concerns that the signals might be caused by instrumental artifacts or background contamination from nearby eclipsing binary systems. However, detailed analysis of the signal characteristics confirmed that the transits were indeed caused by a single planet orbiting the Kepler-16 binary system. The variations in transit timing and depth matched theoretical predictions for a circumbinary planet, and the overall pattern of transits showed the long-term stability expected for a genuine planetary system. The discovery of Kepler-16b required not just sophisticated data analysis techniques, but also new theoretical frameworks for understanding planetary dynamics in binary star systems. Traditional models of planetary orbits, developed for single-star systems like our own solar system, were inadequate for describing the complex gravitational environment of a circumbinary planet. Gently, we discover that the analysis of Kepler-16b pushed the boundaries of celestial mechanics, requiring astronomers to develop new computational methods for modeling three-body gravitational systems where all objects are in motion around their common center of mass. These models had to account not only for the gravitational attraction between the planet and each star, but also for the time-varying gravitational field created by the orbital motion of the binary stars themselves. The success of these theoretical developments validated our understanding of gravitational dynamics and demonstrated the power of modern computational methods to solve previously intractable problems in celestial mechanics. The accurate prediction of Kepler-16b's transit characteristics using these models provided strong confirmation that the observed signals were indeed caused by a genuine circumbinary planet. The Kepler mission's impact extended far beyond the discovery of individual planets like Kepler-16b. By providing the first comprehensive statistical survey of planetary systems in our galaxy, Kepler revealed fundamental patterns in planetary formation and evolution that had been hidden from previous, more limited surveys. The mission discovered that small planets are much more common than large planets, that planets with sizes between Earth and Neptune, a class not represented in our solar system, are actually the most common type of planet in the galaxy, and that planetary systems with multiple planets in compact configurations are surprisingly common. Like whispers in the night, these statistical insights emerged gradually from the accumulation of hundreds, then thousands of planet discoveries. Each new planet added to our understanding of the processes that shape planetary systems, revealing patterns that could only be discerned through large-scale statistical analysis. The discovery of circumbinary planets like Kepler-16b represented one of the most unexpected and significant results of the Kepler mission. Before these discoveries, many astronomers believed that the gravitational perturbations in binary star systems would prevent stable planetary orbits from forming or surviving over cosmic timescales. The existence of these worlds forced a fundamental revision of our theories of planetary formation in binary systems and opened up new avenues of research into the dynamics of multibody gravitational systems. It also significantly expanded the number of potentially habitable environments in our galaxy. Since binary star systems represent roughly half of all stellar systems, in the quiet space of scientific revolution, the Kepler mission transformed exoplanet science from a field focused on detecting individual worlds to one capable of studying the statistical properties of planetary populations throughout the galaxy. This transformation laid the groundwork for current and future missions that will characterize the atmospheres and compositions of exoplanets, potentially even detecting signs of life on distant worlds. The legacy of the Kepler mission extends to the development of new technologies and analysis techniques that continue to benefit astronomical research. The methods developed for Kepler data analysis have been adapted for use with other space missions, including the transiting exoplanet survey satellite tests and the upcoming James Webb Space Telescope. The mission also demonstrated the power of international collaboration in advancing our understanding of the cosmos. The analysis of Kepler data involved hundreds of scientists from dozens of countries, each contributing their expertise to the common goal of understanding planetary systems throughout the galaxy. The precision photometry techniques pioneered by Kepler have applications beyond exoplanet science. The same methods used to detect planetary transits have been adapted to study stellar oscillations, stellar rotation, magnetic activity cycles, and binary star evolution opening up new frontiers in stellar astrophysics. Gently, we discover that the Kepler mission's most profound contribution may be its demonstration that planets are not rare exceptions in the cosmos, but rather common features of stellar systems throughout our galaxy. This realization has fundamentally changed our perspective on our place in the universe and has renewed interest in the search for life beyond Earth. The gentle precision of Kepler's observations revealed a universe far richer and more diverse than we had previously imagined. From hot Jupiters orbiting their stars in mere days to circumbinary worlds, like Kepler-16b experiencing the light of two suns, the mission showed us that planetary systems exhibit an almost limitless variety of configurations and characteristics. As we reflect on the Kepler mission's contributions to our understanding of Kepler-16b and countless other worlds, we are reminded of the power of patient observation and careful analysis to reveal the hidden wonders of the cosmos. Like whispers in the night, the faint signals detected by Kepler continue to inform our understanding of planetary formation, evolution, and the potential for life throughout the galaxy. Now we float toward a deeper understanding of the stellar environment that makes Kepler-16b possible, the fascinating world of binary star systems, where gravitational forces create cosmic dances that have continued for billions of years. In the gentle embrace of space, we'll explore how two stars can share their existence in such perfect harmony that they can nurture worlds in the space between them. In the quiet space of the cosmos, more than half of all stars do not shine alone. Instead, they exist in gravitational partnerships with one or more stellar companions, creating binary and multiple star systems that perform intricate orbital dances across the vast stage of space. These stellar partnerships, far from being rare cosmic curiosities, represent one of the most common configurations of matter in our galaxy. The Kepler-16 system exemplifies the elegant simplicity of a close binary star system, where two stars orbit their common center of mass, their barycenter, in a cosmic waltz that has continued unchanged for billions of years. Gently, we discover that this gravitational partnership creates conditions that are simultaneously more complex and more stable than we might initially expect, providing a suitable environment for planetary formation and long-term orbital stability. Binary star formation begins in the cold, dense regions of molecular clouds, where gravity slowly draws together the gas and dust that will eventually become stars. In many cases, the collapsing material naturally fragments into multiple dense cores, each of which will eventually ignite nuclear fusion and become a star. The initial separation and relative motion of these forming stars determine whether they will remain gravitationally bound as a binary system or drift apart as independent stellar objects. The two stars of the Kepler-16 system likely formed together from the same molecular cloud, approximately 12 billion years ago, condensing from the primordial material that existed in the early galaxy. Their current orbital configuration circling each other every 41.1 days, at an average separation of about 0.22 astronomical units, represents the endpoint of a complex evolutionary process that began when both stars were still contracting protostars surrounded by disks of gas and dust. Like whispers in the night, the gravitational interactions between forming binary stars and their surrounding material disks leave subtle signatures that we can still detect billions of years later. The orbital characteristics of the mature binary system, the properties of any planets that formed from the disk material, and even the rotational periods of the individual stars, all carry information about the conditions that existed during the system's youth. Kepler-16a, the primary star in the system, is what astronomers classify as a K-type dwarf star, with a mass approximately 69% that of our Sun and a radius about 65% of the solar radius. This star shines with a gentle orange light that would give any nearby world a perpetual sunset glow. Its surface temperature of approximately 4,450 Kelvin makes it cooler and less luminous than our Sun, contributing about 84% of the total light output of the binary system. The secondary star, Kepler-16b, is significantly smaller and dimmer than its companion. This M-type red dwarf has a mass only 20% that of our Sun and a radius just 16% of the solar radius. Its surface temperature of approximately 3,311 Kelvin gives it a deep red color, and it contributes only about 16% of the system's total luminosity despite representing about 1/4 of the system's total mass. In the quiet space of stellar evolution, these two stars represent different stages along the main sequence, the long, stable phase of stellar evolution during which stars fuse hydrogen into helium in their cores. The more massive primary star will evolve more quickly, exhausting its core hydrogen and beginning its evolution toward the red giant phase, while its smaller companion continues main sequence hydrogen burning for tens of billions of years. The orbital dynamics of the Kepler-16 binary system demonstrate the elegant principles of celestial mechanics on a cosmic scale. The two stars follow elliptical orbits around their barycenter, the point, where their gravitational forces balance with an orbital eccentricity of 0.16. This orbital motion creates the regular pattern of eclipses that first drew astronomers' attention to the Kepler-16 system. Every 41.1 days, the orbital geometry aligns such that one star passes in front of the other as seen from Earth, creating deep dimming events that can reduce the system's total brightness by several percent. These eclipses alternate between primary eclipses when the smaller, dimmer star passes behind the larger, brighter star, and secondary eclipses when the dimmer star transits across the face of the brighter star. Gently, we discover that the precise timing and depth of these eclipses carry detailed information about the physical properties of both stars. By measuring how long each eclipse lasts and how much the system dims during each event, astronomers can determine the sizes, masses, surface temperatures, and orbital characteristics of both stars with remarkable precision. The analysis of eclipsing binary light curves represents one of the most powerful methods in all of astronomy for determining fundamental stellar properties. Unlike single stars, whose masses can only be estimated indirectly through theoretical models, the orbital motion of binary stars provides a direct measurement of stellar masses through the application of Newton's laws of gravitation. For the Kepler-16 system, this analysis revealed that the primary star has a mass of 0.6897 solar masses and a radius of 0.6489 solar radii, while the secondary star has a mass of 0.2026 solar masses and a radius of 0.226 solar radii. These measurements are among the most precise stellar mass and radius determinations ever made, with uncertainties of less than 1% in most cases. The gravitational field created by this binary system extends far beyond the immediate vicinity of the two stars themselves. At the location of Kepler-16b's orbit, approximately 0.7 astronomical units from the binary's center of mass, the planet experiences gravitational forces from both stars that vary in strength and direction as the stars complete their orbital motion around the barycenter. Like whispers in the night, these varying gravitational forces create subtle perturbations in the planet's orbit that would be impossible in a single star system. The planet's orbital speed varies slightly as it moves around its elliptical path, and the orientation of its orbit slowly precesses rotating in space over time scales of thousands of years, in response to the time-varying gravitational field of the binary stars. Despite these complexities, the orbit of Kepler-16b remains remarkably stable over cosmic timescales. Theoretical calculations show that the planet's current orbit lies well outside the dynamical instability zone, where gravitational perturbations from the binary stars would cause orbital chaos and potentially eject the planet from the system entirely. This stability is crucial for understanding how planets can form and survive in binary star systems. During the early phases of planetary system formation, when small planetesimals are gradually accumulating into larger planetary bodies, orbital stability is essential for allowing the accretion process to continue over the millions of years required to build planets. The formation of planets in binary star systems presents unique challenges compared to planet formation around single stars. The gravitational influence of two stars creates a more complex environment for the protoplanetary disk of gas and dust from which planets form, depending on the separation and masses of the binary stars. This influence can either enhance or inhibit the planet formation process. In the quiet space of the early solar system, gravitational torques from the binary stars can cause the protoplanetary disk to become warped or truncated, potentially affecting the distribution of solid material available for planet formation. In some cases, these effects might prevent planet formation entirely, while in others they might lead to the formation of planetary systems, with characteristics quite different from those around single stars. For systems like Kepler-16, where the binary stars are relatively close together compared to the planet's orbital distance, the protoplanetary disk likely extended well beyond the current location of Kepler-16b. Material in the inner regions of the disk, close to the binary stars, would have been subject to strong gravitational perturbations that could have prevented planet formation or caused any forming planets to spiral into the stars. However, at the distance where Kepler-16b currently orbits, the gravitational environment would have been sufficiently stable to allow normal planetary accretion processes to occur. The planet likely formed through the same general process that created the gas giants. In our own solar system, the gravitational collapse of a massive envelope of hydrogen and helium gas onto a solid core of rock and ice. The timing of this formation process was crucial for the planet's ultimate characteristics. If Kepler-16b formed too early, while the protoplanetary disk still contained large amounts of gas, it might have continued accreting material and become much more massive if it formed too late, after the gas had been dispersed by stellar winds and radiation. It might have remained as a rocky planet rather than developing into a gas giant. Gently, we discover that the current mass and composition of Kepler-16b, approximately 105 Earth masses with a composition dominated by hydrogen and helium, suggests that its formation occurred during a specific window of time when conditions in the protoplanetary disk were optimal for gas giant formation. The study of binary star systems like Kepler-16 has revealed that stellar multiplicity is far more common than was once believed. Surveys of nearby stars suggest that at least 50% of Sun-like stars exist in binary or multiple star systems, with the percentage being even higher for more massive stars. This high frequency of stellar multiplicity has profound implications for our understanding of star formation and planetary system architecture throughout the galaxy. Different types of binary systems create different environments for planet formation and evolution. Wide binary systems, where the stars are separated by hundreds or thousands of O, have minimal influence on planetary formation around either star, and planets in such systems behave much like planets in single-star systems. Close binary systems, like Kepler-16, prevent stable planetary orbits around either individual star but can support stable circumbinary orbits around both stars. Intermediate separation binary systems present the most complex case, where planets might be able to orbit either individual star in so-called S-type orbits, or both stars in P-type or circumbinary orbits, depending on the specific orbital characteristics of the binary and the dynamical history of the planetary system. Like whispers in the night, the gravitational dynamics of these different binary configurations create distinct observational signatures that allow astronomers to distinguish between different types of planetary systems even when the planets themselves are not directly detectable. The analysis of stellar motion, eclipse timing variations, and other subtle effects can reveal the presence of planets in binary systems, even when traditional detection methods fail. The discovery of circumbinary planets like Kepler-16b has opened up new avenues of research into the dynamics of multi-body gravitational systems. Traditional celestial mechanics developed primarily for single-star planetary systems must be extended to handle the more complex case of planets orbiting binary stars where the gravitational field varies both in strength and direction over the orbital period of the binary. This extension requires sophisticated numerical integration techniques and careful consideration of gravitational resonances, tidal effects, and other perturbations that can affect planetary orbits over long time scales. The development of these theoretical frameworks has not only advanced our understanding of circumbinary planets, but has also contributed to our broader understanding of gravitational dynamics in complex multi-body systems. The study of binary stars also provides unique insights into stellar evolution and the long-term fate of planetary systems. In close binary systems, the two stars can interact through mass transfer, tidal effects, and magnetic field interactions that significantly alter their evolutionary paths, compared to single stars of similar mass. In the quiet space of cosmic time, these interactions can lead to phenomena such as common envelope evolution, where one star engulfs its companion, or type E supernovae, where mass transfer onto a white dwarf star triggers a thermonuclear explosion. Understanding these evolutionary processes is crucial for predicting the long-term habitability of planets in binary systems and for interpreting observations of evolved binary systems throughout the galaxy. For the Kepler-16 system, stellar evolution will play out over time scales of billions of years. The more massive primary star will eventually exhaust the hydrogen in its core and begin evolving into a red giant, dramatically increasing in size and luminosity. This evolution will fundamentally alter the radiation environment experienced by Kepler-16b and could potentially affect the planet's atmospheric composition and thermal structure. The less massive secondary star will continue main sequence hydrogen burning for tens of billions of years, potentially outliving the primary star and continuing to provide energy to the system long after the primary has evolved into a white dwarf. This extended stellar lifetime raises interesting questions about the long-term evolution of planetary atmospheres and the potential for complex chemical processes to operate over cosmic timescales. The electromagnetic radiation environment in binary star systems differs significantly from that in single-star systems. Planets like Kepler-16b receive light from two sources with different spectral characteristics, creating a combined spectrum that varies as the relative positions of the stars change over their orbital period. Gently, we discover that this varying spectral environment could have profound effects on atmospheric chemistry and dynamics in any planets that possess substantial atmospheres. Photochemical reactions that are driven by stellar ultraviolet radiation would respond to the combined and varying UV output of both stars, potentially creating atmospheric compositions quite different from those found in single-star systems. The thermal environment of circumbinary planets is also more complex than that of planets around single stars. The total energy received by the planet varies as the binary stars move through their orbital dance, and the spatial distribution of heating on the planet's surface depends on the relative positions and angular sizes of the two stars as seen from the planet. During some parts of the binary orbital period, both stars might be visible simultaneously from the planet, creating complex patterns of illumination and shadow. At other times, one star might eclipse the other as seen from the planet, temporarily reducing the total energy input and potentially creating unique atmospheric circulation patterns. In response to these periodic variations in heating, these thermal variations occur on the time scale of the binary orbital period, 41.1 days for Kepler-16, which is much shorter than the planet's orbital period of 229 days. This creates a complex interplay between the planet's seasonal variations, driven by its orbital motion around the binary, and the shorter-term variations driven by the orbital motion of the binary stars themselves. Like whispers in the night, these multiple cycles of variation would create atmospheric dynamics unlike anything found in our own solar system. Computer models of such atmospheres are still in their infancy, but they suggest that circumbinary planets might exhibit unique weather patterns and atmospheric circulation systems that reflect the complex temporal variations in stellar heating. The study of binary star systems has also revealed important insights into the process of stellar formation itself. The orbital characteristics of binary systems carry information about the conditions that existed in the molecular cloud from which the stars formed, including the density, temperature, and turbulent motion of the primordial gas. Statistical studies of binary orbital periods, eccentricities, and mass ratios have shown that there are preferred configurations that reflect the physics of the star formation process. Close binary systems like Kepler-16 are thought to form through the fragmentation of dense cores in molecular clouds, while wider binary systems might form through the capture of initially unbound stars in stellar clusters. The orbital characteristics of the Kepler-16 binary, particularly its circular orbit, and the fact that both stars are roughly aligned in the same plane as the planetary orbit suggests that this system formed through a relatively gentle process that preserved the angular momentum of the original molecular cloud core. More violent formation processes would likely have resulted in more eccentric orbits or misaligned stellar rotation axes. In the quiet space of stellar evolution, the Kepler-16 system represents a kind of cosmic fossil, preserving information about the conditions that existed in our galaxy over 12 billion years ago. By studying the detailed properties of this system, the masses and compositions of its stars, the characteristics of its planet, and the dynamics of their orbital interactions, we gain insights into the processes that have shaped our galaxy throughout cosmic history. The discovery of planets in binary star systems has also expanded our understanding of the potential diversity of habitable environments in the universe. While Kepler-16b itself is too cold and gaseous to support life as we know it, the existence of stable planetary orbits in binary systems suggests that Earth-like worlds might also exist in such environments. A terrestrial planet in the habitable zone of a binary system like Kepler-16 would experience a uniquely complex environment with varying levels of stellar radiation, complex seasonal cycles, and spectacular views of binary sunrises and sunsets. Such a world would challenge our assumptions about the conditions necessary for the origin and evolution of life and might harbor forms of life adapted to the unique characteristics of a binary star environment. As our journey continues, we begin to appreciate the remarkable fact that stable planetary systems can exist and thrive in the gravitationally complex environment of binary star systems. The discovery of Kepler-16b and other circumbinary planets has revealed that the universe is even more hospitable to planetary formation than we previously imagined, with stable orbits possible in stellar configurations that make up roughly half of all stars in our galaxy. Gently, we discover that the principles of celestial mechanics, first developed to understand the motions of planets in our own solar system, apply with equal elegance to the more complex choreography of worlds orbiting binary stars. The gravitational forces that seemed to pose insurmountable obstacles to planetary formation actually create new opportunities for stable, long-lived planetary systems with characteristics unlike anything in our cosmic neighborhood. Let's drift into the specific moment of discovery, when the careful analysis of Kepler's photometric data revealed the unmistakable signature of a world orbiting not one but two stars. In the gentle flow of scientific discovery, we'll explore how astronomers first recognized the unique characteristics of Kepler-16b's transits and confirmed the existence of this remarkable circumbinary world. In the quiet space of scientific discovery, some of the most profound revelations come not with fanfare and drama, but through the patient accumulation of data and the gradual recognition of patterns that reveal new truths about the cosmos. The discovery of Kepler-16b exemplifies this gentle process of revelation, emerging from months of careful analysis of subtle light variations detected by the Kepler Space Telescope. The story begins with the Kepler mission's systematic survey of stellar brightness variations in its target field in the constellation Cygnus. Among the more than 150,000 stars monitored by Kepler, the binary system now known as Kepler-16 initially attracted attention, not for any planetary signals but for the deep regular eclipses that occur as the two stars orbit around their common center of mass. These binary eclipses were immediately recognizable in the Kepler photometric data. Every 41.1 days, the combined light from the system would dim by several percent as the smaller, dimmer star passed behind the larger, brighter star, and then dim again by a smaller amount about 20 days later as the smaller star transited across the face of the larger star. This regular pattern of primary and secondary eclipses clearly identified Kepler-16 as an eclipsing binary star system. Gently, we discover that the analysis of eclipsing binary systems was already a well-established branch of astronomy, with techniques developed over more than a century for extracting stellar properties from eclipse-like curves. The Kepler team's initial analysis of the Kepler-16 system focused on using these traditional methods to determine the masses, radii, and orbital characteristics of both stars. However, As the analysis progressed and more data accumulated, subtle anomalies began to appear in the light curve that couldn't be explained by the simple model of two stars eclipsing each other. These anomalous signals initially posed a puzzle for the analysis team. The events were too shallow and too brief to be caused by additional stellar companions, but they were too deep and too regular to be attributed to instrumental noise or stellar variability. The irregular timing of these events was particularly puzzling, as it didn't match any obvious periodic pattern that might be expected from a simple astronomical phenomenon. Like whispers in the night, these subtle signals carried information that would revolutionize our understanding of planetary systems, but their true significance only became apparent through careful analysis and theoretical modeling. The breakthrough came when astronomers realized that the irregular timing of the events could be explained if they were caused by a planet whose orbit carried it alternately in front of each of the two stars in the binary system. The concept of a circumbinary planet or world orbiting both stars of a binary system had been discussed theoretically for decades, but no such planets had been definitively detected using the transit method. The irregular timing of planetary transits in such a system results from the constantly changing positions of the binary stars, which create a complex, time-varying gravitational field that affects the planet's orbital motion. Unlike planets in single-star systems, where transits occur at perfectly regular intervals determined by the planet's orbital period, a circumbinary planet experiences gravitational perturbations that cause slight variations in its orbital speed and path. These variations, while small, are sufficient to create the irregular transit timing that was observed in the Kepler-16 data. In the quiet space of theoretical analysis, the team began developing sophisticated computer models to test whether a circumbinary planet could indeed explain the observed light curve anomalies. These models had to account for the gravitational interactions between all three objects, the two stars and the hypothetical planet, as well as the complex geometry of a system where the planet might sometimes transit one star, sometimes the other, and sometimes both stars simultaneously. The modeling process required advanced numerical integration techniques to calculate the precise orbital motion of a planet in the time-varying gravitational field of the binary stars. Unlike the simple elliptical orbits followed by planets around single stars, the orbit of a circumbinary planet is constantly perturbed by the changing positions of its host stars, creating subtle variations in orbital speed and direction that accumulate over multiple orbital periods. As the models became more sophisticated and more data became available from continued Kepler observations, a consistent picture began to emerge. The anomalous dimming events could indeed be explained by a single planet with a mass similar to Saturn, orbiting the binary system at a distance of approximately 0.7 astronomical units from the center of mass. Of the two stars, the planet's orbital period of 229 days meant that it completed one orbit around the binary stars. In the time it took the stars themselves to complete about 5.6 orbits around each other. Gently, we discover that the confirmation of Kepler-16b required not just sophisticated theoretical modeling, but also careful analysis of the statistical significance of the observed signals. The team had to demonstrate that the probability of the observed dimming events being caused by random noise or systematic instrumental effects was extremely low, less than 1 in several million. This statistical analysis involved comparing the observed light curve to thousands of simulated light curves generated with different assumptions about noise levels, systematic effects, and potential astrophysical false positives. Only when all alternative explanations had been ruled out with high confidence could the team claim the discovery of a genuine circumbinary planet. The validation process also included extensive ground-based follow-up observations to confirm the stellar properties of the Kepler-16 system and to search for any additional evidence of planetary companions. These observations used a variety of techniques, including high-resolution spectroscopy to measure the radial velocities of the stars, adaptive optics imaging to search for background contaminating stars, and additional photometry to confirm the Kepler results. One of the most compelling pieces of evidence for the planetary interpretation came from the detailed analysis of transit timing variations. the slight changes in the arrival times of the planetary transits, caused by gravitational perturbations from the binary stars, matched theoretical predictions with remarkable precision. These timing variations were far too complex and systematic to be explained by instrumental effects or random noise, like whispers in the night. The precise agreement between theoretical predictions and observational data provided strong confirmation that the team had indeed discovered the first definitively confirmed circumbinary planet detected by the transit method. The discovery represented a triumph of both observational precision and theoretical understanding, demonstrating the power of combining sensitive space-based photometry with sophisticated gravitational modeling. The announcement of the Kepler-16b discovery in September 2011 marked a watershed moment in exoplanet science. While planets had been discovered around binary star systems before, most notably PSRB 1620-26b, a world orbiting a pulsar white dwarf binary, Kepler-16b was the first such planet detected, using the transit method and the first circumbinary planet around a main sequence binary star system. The discovery validation process took nearly 2 years, from the initial detection of anomalous signals to the final confirmation and publication of results. This extended timeline reflected the unprecedented nature of the discovery and the need for extraordinarily rigorous analysis to ensure that the claimed detection was genuine. During this validation period, the team developed new techniques for analyzing circumbinary transit light curves that would prove invaluable for the discovery and characterization of additional such systems. These techniques included methods for handling the irregular transit timing, algorithms for fitting complex multi-body orbital models to photometric data, and statistical frameworks for assessing the significance of planetary signals in binary star systems. In the quiet space of peer review and scientific scrutiny, the Kepler-16b discovery underwent extensive evaluation by independent experts who verified the analysis methods, checked the statistical significance calculations, and confirmed that all reasonable alternative explanations had been properly considered and ruled out. This rigorous review process is essential for maintaining the credibility of exoplanet discoveries, particularly for unusual systems like Kepler-16b that push the boundaries of our understanding of planetary system architecture. The complexity of circumbinary dynamics makes it especially important to ensure that claimed detections are based on solid observational evidence and robust theoretical analysis. The confirmation of Kepler-16b opened the floodgates for the discovery of additional circumbinary planets. Within a few years of the initial announcement, the Kepler mission had identified several other transiting circumbinary worlds, including Kepler-34b, Kepler-35b, Kepler-38b, Kepler-47b and C, and Kepler-453b. Each of these discoveries further validated the theoretical frameworks developed for Kepler-16b and provided additional insights into the formation and evolution of planetary systems in binary star environments. The discovery also had important implications for our understanding of planetary formation processes. The existence of gas giant planets like Kepler-16 being binary systems suggested that the planet formation process is more robust and adaptable than previously thought, capable of operating effectively even in the gravitationally complex environment of a circumbinary disk. Gently, we discover that the formation of Kepler-16b likely required specific conditions in the protoplanetary disk from which it formed. The planet's current location, while outside the instability zone where gravitational perturbations would prevent stable orbits, suggests that it either formed at its current location or migrated there from a more distant orbit during the early phases of system evolution. The planet's mass and composition approximately 105 Earth masses with a bulk density consistent with a hydrogen-helium-dominated atmosphere provide clues about the timing and mechanism of its formation. The successful accumulation of such a massive gaseous envelope requires that core formation occurred, while the protoplanetary disk still contained substantial amounts of gas, probably within the first few million years of the system's existence. The Discovery team's analysis of Kepler-16b's atmospheric properties, while limited by the available data, suggested that the planet's atmosphere is likely dominated by hydrogen and helium with possible traces of heavier elements. The planet's relatively low density, about 0.96 for grams per cubic centimeter, is consistent with a substantial gaseous envelope surrounding a solid core of rock and ice. The thermal properties of Kepler-16b, inferred from its orbital distance and the luminosities of its host stars, place it well outside the traditional habitable zone where liquid water could exist. On a planetary surface, with estimated equilibrium temperatures ranging from about 200 to 240 Kelvin, 73 to -33 degrees Celsius, the planet is far too cold to support surface liquid water. Even if it possessed a solid surface, like whispers in the night, the discovery of Kepler-16b carried implications that extended far beyond the properties of this single world. By demonstrating that stable planetary orbits are possible in binary star systems, the discovery effectively doubled the number of stellar systems in our galaxy that might harbor planets, significantly expanding the potential sites for planetary formation and potentially the development of life. The discovery also provided crucial validation for theoretical models of planetary dynamics. In multi-body gravitational systems, the successful prediction of Kepler-16b's transit characteristics using n-body gravitational simulations demonstrated that our understanding of celestial mechanics is sufficiently sophisticated to handle even the complex case of circumbinary planetary systems. This validation has important implications for our ability to predict the long-term stability and evolution of newly discovered circumbinary worlds. The same theoretical frameworks that successfully described Kepler-16b's orbital dynamics can be applied to assess the stability of other circumbinary systems and to predict how these systems will evolve over cosmic timescales. The discovery process for Kepler-16b also highlighted the importance of automated data analysis techniques in modern astronomy. The initial detection of anomalous signals in the Kepler-16 light curve was made possible by sophisticated algorithms that could process photometric data from thousands of stars, simultaneously identifying subtle patterns that would be impossible to detect through visual inspection alone. In the quiet space of computational astronomy, these automated detection algorithms represent a revolution in our ability to discover and characterize exoplanets. The sheer volume of data produced by modern space-based missions like Kepler makes human analysis of individual stellar light curves impractical, requiring sophisticated machine learning techniques to identify planetary signals buried in the noise. As our journey continues, we drift deeper into contemplation of Kepler-16b itself, this remarkable world that has captured our imagination and expanded our understanding of planetary possibilities. In the quiet space of scientific measurement and theoretical modeling, we begin to construct a detailed portrait of this distant planet, piecing together its characteristics from the subtle whispers of starlight that have traveled to 145 light-years to reach our sensitive instruments. Kepler-16b is what astronomers classify as a gas giant, a world dominated by a thick atmosphere of hydrogen and helium, similar in many respects to Saturn in our own solar system. With a mass approximately 105 times that of Earth, or about one-third the mass of Jupiter, this distant world represents a substantial gravitational presence in its binary star system, massive enough to significantly influence the orbital dynamics of the system, while remaining small enough to maintain a stable circumbinary orbit. Gently, we discover that the planet's radius is approximately 8.5 times that of Earth, making it slightly smaller than Saturn but substantially larger than Neptune. This size places Kepler-16b firmly in the category of gas giants, worlds whose bulk composition is dominated by volatile compounds rather than the rocky materials that characterize terrestrial planets like Earth, Venus, and Mars. The bulk density of Kepler-16b, calculated from its measured mass and radius, is approximately 0.96 for grams per cubic centimeter, remarkably close to the density of water. This low density is characteristic of gas giant planets with substantial atmospheric envelopes, confirming that Kepler-16b possesses a thick layer of gaseous material surrounding whatever solid core might exist at its center. Like whispers in the night, the planet's orbital characteristics reveal the complex gravitational environment in which it resides. Kepler-16b follows an elliptical orbit around the center of mass of the binary star system, completing one full revolution every 228.776 Earth days. This orbital period places the planet well beyond the gravitational instability zone, where tidal forces from the binary stars would make stable planetary orbits impossible. The planet's average orbital distance from the binary center of mass is approximately 0.708 astronomical units, roughly 70% of the distance between Earth and the Sun. However, due to the elliptical nature of its orbit, Kepler-16b's distance from the binary stars varies between about 0.599 astronomical units at periastron, closest approach, and 0.810 astronomical units at apastron, maximum distance. In the quiet space of orbital mechanics, this variation in distance creates complex thermal cycles on the planet. As Kepler-16b follows its elliptical path, the amount of stellar radiation it receives changes by approximately 80% between periastron and apastron. This variation is much more dramatic than the small changes experienced by planets in our solar system, adding another layer of complexity to the planet's atmospheric dynamics. The orbital inclination of Kepler-16b, the angle between its orbital plane and our line of sight from Earth, is approximately 90.03 degrees. This nearly edge-on orientation is what makes the planet's transits visible from Earth, allowing us to detect the periodic dimming of starlight as the planet passes in front of its host stars. Without this fortunate geometric alignment, Kepler-16b would remain invisible to transit detection methods, hidden among the countless stars of the Milky Way. Let's drift into consideration of the planet's atmospheric properties, which we can infer from its mass, radius, and thermal environment. Given its size and density, Kepler-16b almost certainly possesses a substantial atmosphere dominated by hydrogen and helium, the lightest and most abundant elements in the universe. The atmospheric composition likely includes traces of heavier elements and compounds, possibly including water vapor, methane, and ammonia molecules, that are common in the outer regions of planetary systems where temperatures are low enough for these compounds to condense from the gaseous phase. However, the precise composition of Kepler-16b's atmosphere remains largely unknown, as current observational techniques are not sensitive enough to detect atmospheric spectral features. In circumbinary planets, gently, we discover that the planet's atmospheric structure is likely influenced by the complex radiation environment created by its binary host stars. Unlike planets orbiting single stars, which receive relatively uniform stellar radiation, Kepler-16b experiences varying illumination as the two stars move through their orbital dance, creating complex patterns of heating and cooling in different parts of the atmosphere. The temperature structure of Kepler-16b's atmosphere is particularly intriguing. Theoretical models suggest that the planet's equilibrium temperature, the temperature it would have if it were a perfect absorber and radiator of energy, ranges from about 200 to 240 Kelvin, 73 to -33 degrees Celsius, depending on assumptions about the planet's atmospheric properties and albedo. This temperature range places Kepler-16b well outside the traditional habitable zone where liquid water could exist on a planetary surface. However, the concept of habitability in gas giant planets is more complex than for terrestrial worlds, as gas giants lack solid surfaces where liquid water could pool. Instead, scientists consider the possibility of habitable conditions in the atmospheres of gas giants or on any large moons that might orbit them. Like whispers in the night, the atmospheric dynamics of Kepler-16b are likely dominated by complex circulation patterns, driven by the varying stellar heating from its binary host stars. As the planet orbits the binary system, different hemispheres experience different levels of illumination, creating temperature gradients that drive atmospheric winds and weather systems. The planet's atmospheric circulation is also influenced by its rotation period, which unfortunately cannot be measured directly with current observational techniques. However, theoretical models suggest that gas giants in circumbinary orbits may experience complex rotational dynamics due to tidal forces from their host stars, potentially leading to synchronous or pseudosynchronous rotation where the planet's rotation period becomes coupled to its orbital period. in the quiet space of comparative planetology. Kepler-16b offers fascinating contrasts with the gas giants of our own solar system. While Saturn, the most similar planet in terms of mass and density, orbits a single star in a relatively circular orbit, Kepler-16b experiences the complex gravitational environment of a binary system and follows a more elliptical path. These differences have profound implications for the planets, atmospheric dynamics, thermal evolution, and potential for hosting moon systems. The gravitational perturbations from the binary stars create a more complex tidal environment than exists in our solar system, potentially affecting the long-term stability of any satellite systems that might orbit Kepler-16b. The magnetic field of Kepler-16b, if it exists, would be generated by the same dynamo processes that create magnetic fields in other gas giant planets. Convective motion in a conducting fluid interior, typically liquid metallic hydrogen. The strength and structure of this magnetic field would depend on the planet's internal structure, rotation rate, and the composition of its deep interior. Gently, we discover that a magnetic field would play a crucial role in shaping the planet's interaction with the stellar winds from its binary host stars. Unlike planets orbiting single stars, which experience relatively steady stellar wind conditions, Kepler-16b would encounter varying particle fluxes as the binary stars move through their orbital cycle, creating complex magnetospheric dynamics. The internal structure of Kepler-16b likely resembles that of other gas giant planets, with a solid core of rock and ice surrounded by layers of liquid and gaseous hydrogen and helium. The exact size and composition of this core depend on the planet's formation history and the conditions in the protoplanetary disk from which it formed. Theoretical models suggest that the core of Kepler-16b could contain anywhere from 10 to 50 Earth masses of solid material, composed primarily of rock-forming elements like silicon, magnesium, and iron, along with substantial amounts of water, ice, and other volatile compounds that were able to condense at the planet's formation distance from its host stars, like whispers in the night. The formation of this core would have been a gradual process, with solid particles in the protoplanetary disk slowly accumulating through gravitational attraction and collisional aggregation. Once the core reached a critical mass, probably around 10 to 15 Earth masses, it would have begun rapidly accreting gas from the surrounding disk, eventually building up the massive atmospheric envelope that characterizes the planet today. The timing of this gas accretion phase is crucial for understanding Kepler-16b's current properties. The planet must have completed its formation while the protoplanetary disk still contained substantial amounts of gas, probably within the first 10 million years of the system's existence. After this time, stellar winds and other dispersal mechanisms would have cleared most of the gas from the disk, preventing further atmospheric growth. Now we float toward consideration of Kepler-16b's potential for hosting moon systems, a topic of particular interest. Given the rich satellite systems of gas giants in our own solar system, Jupiter and Saturn each host dozens of moons, ranging from small irregular captured asteroids to large, geologically active worlds like Europa, Enceladus, and Titan. The question of whether Kepler-16b could maintain stable moon systems is complex, involving the competing gravitational influences of the planet itself and the binary star system around which it orbits. The Hill sphere, the region around the planet where its gravity dominates over tidal forces from the stars, determines the maximum distance at which stable satellite orbits are possible. In the quiet space of celestial mechanics, the Hill sphere radius of Kepler-16b is significantly smaller than would be the case for a similar mass planet orbiting a single star. The complex gravitational environment of the binary system reduces the region of gravitational dominance around the planet, limiting the possible orbital distances for any potential moons. Theoretical calculations suggest that stable satellite orbits around Kepler-16b would be restricted to distances of less than about 0.5% of the planet's orbital radius around the binary stars. This constraint would allow for moon systems similar to the inner satellites of Jupiter or Saturn, but would preclude the existence of satellites at distances comparable to Jupiter's Galilean moons, or Saturn's major satellites like Titan and Iapetus. Despite these constraints, the possibility of satellite systems around Kepler-16b remains scientifically intriguing. Large moons orbiting gas giant planets in habitable zones around binary stars could, in principle, provide environments suitable for the development and maintenance of liquid water, and potentially even life. Gently, we discover that the detection of moons around circumbinary planets like Kepler-16b represents one of the most challenging frontiers in current exoplanet science. The observational signatures of such moons would be extremely subtle, requiring observational precision that pushes the limits of current technology. The gravitational influence of large moons would cause slight variations in the timing and duration of the planet's transits across its host star's variations that might be detectable with extremely precise photometry and careful analysis of transit timing variations. However, separating the effects of satellite-induced timing variations from the much larger timing variation caused by gravitational perturbations from the binary stars remains a formidable challenge. The atmospheric escape processes on Kepler-16b provide another avenue for understanding the planet's evolution and current state. Gas giant planets, particularly those at relatively close orbital distances from their host stars, can lose atmospheric material through several mechanisms, including thermal escape, photoevaporation, and mass loss driven by stellar winds. Like whispers in the night, the atmospheric escape from Kepler-16b is likely influenced by the complex radiation environment created by its binary host stars. The planet experiences varying levels of high-energy radiation as the two stars move through their orbital cycle, creating time-variable photoevaporation rates that add complexity to theoretical models of atmospheric evolution. The hydrodynamic escape of atmospheric material from Kepler-16b is probably minimal, given the planet's substantial mass and the relatively modest levels of stellar irradiation it receives. The planet's escape velocity, approximately 20 kilometers per second, is sufficiently large that thermal motion alone cannot drive significant atmospheric loss, even for the lightest atmospheric constituents like hydrogen and helium. However, more sophisticated escape mechanisms, such as photoevaporation driven by stellar X-ray and extreme ultraviolet radiation, could still play a role in the planet's atmospheric evolution. The combined X-ray and EUV output of the binary system would heat the upper atmosphere of Kepler-16b, potentially driving a hydrodynamic outflow of atmospheric material. In the quiet space of atmospheric modeling, scientists estimate that Kepler-16b has likely retained the vast majority of its original atmospheric envelope. Over the 4.6 billion-year lifetime of the system, the planet's location well outside the habitable zone and its substantial gravitational field provide protection against significant atmospheric loss, ensuring that its current properties probably closely resemble those it possessed shortly after formation. The seasonal variations on Kepler-16b, while not true seasons in the terrestrial sense, would be driven by the planet's elliptical orbit and the complex orbital dynamics of the binary star system. As the planet moves through its 229-day orbit, it experiences varying levels of stellar irradiation due to changes in its distance from the binary stars and changes in the relative positions of the two stars. These variations would create complex patterns of atmospheric heating and cooling, potentially driving large-scale circulation patterns and weather systems unlike anything observed in our solar system. The planet's thick atmosphere would help moderate these variations through thermal inertia, but significant seasonal effects would still be expected, particularly in the upper atmospheric layers where radiative heating and cooling dominate. Gently, we discover that the study of Kepler-16b's atmospheric dynamics requires sophisticated three-dimensional climate models that can account for the time-varying stellar illumination patterns created by the binary host stars. These models must consider not only the changing total amount of stellar radiation received by the planet, but also the varying spectral characteristics of the radiation as the relative contributions of the two stars change throughout the orbital cycle. The cloud formation processes on Kepler-16b would be particularly complex, involving the condensation of various atmospheric constituents at different altitudes and temperatures within the planet's atmospheric column. Water vapor, ammonia, and hydrocarbon compounds could all potentially form cloud systems in different regions of the atmosphere, creating complex layered structures that would influence the planet's optical properties and thermal balance. The interaction between Kepler-16b and the stellar winds from its binary host stars represents another fascinating aspect of the planet's environment. Unlike planets orbiting single stars, which typically experience relatively steady stellar wind conditions, Kepler-16b would encounter varying particle fluxes and magnetic field strengths as the binary stars move through their orbital cycle. Like whispers in the night, these varying stellar wind conditions would create complex magnetospheric dynamics around Kepler-16b, potentially generating auroral displays and other electromagnetic phenomena unlike anything observed in our solar system. The planet's magnetosphere, if it exists, would be constantly reconfiguring itself in response to the changing stellar wind environment. The radiation environment around Kepler-16b is also of interest for understanding the planet's atmospheric chemistry and potential habitability. The combined stellar output of the binary system includes not only visible light and infrared radiation, but also higher energy photons in the ultraviolet, X-ray, and possibly gamma-ray portions of the electromagnetic spectrum. These high-energy photons can drive complex photochemical reactions in the planet's upper atmosphere, potentially creating exotic atmospheric constituents that would not form under the milder radiation conditions experienced by planets in our solar system. The varying stellar radiation environment would also create time-dependent photochemical processes, adding another layer of complexity to atmospheric models. As our journey continues, we begin to appreciate the remarkable complexity and uniqueness of Kepler-16b as a planetary world. This distant gas giant represents not just a single exotic planet, but an entire class of circumbinary worlds that may be common throughout our galaxy, each one offering its own unique combination of orbital dynamics, atmospheric processes, and environmental conditions. Let's drift into the gentle complexity of gravitational physics that governs the Kepler-16 system, where three massive objects, two stars and one planet, engage in an eternal cosmic dance, guided by the fundamental forces of nature. In the quiet space of mathematical physics, we find a realm where Newton's laws of motion and universal gravitation create intricate patterns of orbital motion that challenge our intuition and expand our understanding of celestial mechanics. The gravitational dynamics of the Kepler-16 system represent what physicists call a hierarchical triple system, where two stars orbit each other in a close binary configuration while a third object, the planet, orbits both stars at a much greater distance. This arrangement creates a natural separation of timescales, with the stellar binary completing many orbits around each other during each single orbit of the planet around the system's center of mass. Gently, we discover that the mathematical description of such systems requires sophisticated numerical techniques to solve what physicists call the restricted three-body problem, unlike the simple two-body problem of a planet orbiting a single star, which has exact analytical solutions. The motion of a planet in a binary star system involves complex interactions between multiple gravitational sources that change continuously as the system evolves. The center of mass of the Kepler-16 binary system, around which the planet orbits, is not located at a fixed point in space, but rather follows a small elliptical path as the two stars orbit each other. This creates a time-varying gravitational potential that the planet experiences as it moves through its own orbit, leading to subtle but measurable perturbations in its orbital elements. The masses of the two stars in the Kepler-16 system play crucial roles in determining the overall gravitational architecture. Kepler-16a, the more massive of the pair, contains approximately 69% of a solar mass, while its companion Kepler-16b contains about 20% of a solar mass. Together, these two stars create a combined gravitational field that the planet must navigate as it maintains its stable circumbinary orbit. Like whispers in the night, the gravitational influence of each star varies as the planet moves through its orbit, and as the stars themselves move through their binary dance. When the planet is at certain points in its orbit, it may be closer to one star than the other, experiencing stronger gravitational acceleration from the nearer star, and creating asymmetries in its orbital motion. The concept of orbital resonances plays an important role in understanding the stability of circumbinary planetary systems like Kepler-16. Orbital resonances occur when the orbital periods of different objects in a system are related by simple integer ratios, creating periodic gravitational perturbations that can either stabilize or destabilize orbital motion depending on the specific circumstances. In the quiet space of dynamical astronomy, the orbital period ratio between Kepler-16b and the stellar binary is approximately 5.6 to 1, meaning that the planet completes one orbit around the binary for every 5.6 orbits that the stars complete around each other. This ratio places the planet well away from the strongest dynamical resonances that could lead to orbital instability. The gravitational perturbations experienced by Kepler-16b create measurable variations in its orbital elements over time. These variations include changes in the planet's orbital eccentricity, semi-major axis inclination, and other orbital parameters. While these changes are typically small over short time scales, they accumulate over longer periods and provide important information about the gravitational architecture of the system. One of the most significant perturbation effects in the Kepler-16 system is the precession of the planet's orbital plane. The gravitational torque exerted by the binary stars causes the plane of the planet's orbit to slowly rotate in space, completing one full precession cycle over a period of approximately 40,000 years. This precession affects the timing and geometric properties of the planet's transits, as observed from Earth. Gently, we discover that the apsidal precession of Kepler-16b's orbit, the rotation of the elliptical orbit within its own plane, occurs on a much shorter time scale of approximately 300 years. This relatively rapid precession is caused by the non-spherical gravitational potential created by the binary stars, which creates a torque on the planet's elliptical orbit that causes its orientation to change over time. The nodal precession of the system, the rotation of the orbital plane around the line connecting the Earth and the binary system, affects the long-term visibility of planetary transits. From our vantage point, over thousands of years, this precession will eventually cause the planet's orbital plane to become misaligned with our line of sight, making transits invisible until the precession brings the system back into alignment. The tidal forces in the Kepler-16 system create additional complexity in the gravitational dynamics. These forces arise from the differential gravitational acceleration experienced by different parts of each object due to their finite size and the varying distance to the gravitational sources. For the planet, tidal forces from both stars contribute to the overall tidal field, creating a complex pattern of distortion that depends on the relative positions of all three objects. Like whispers in the night, these tidal forces are generally much weaker than the primary gravitational acceleration that keeps the planet in orbit, but they can still have important effects over long time scales. Tidal heating, caused by the periodic flexing of the planet's interior due to tidal forces, could contribute to the planet's internal energy budget and influence its thermal evolution. The stability analysis of circumbinary planetary orbits requires sophisticated numerical simulations that integrate the equations of motion over millions of orbital periods to determine whether small perturbations will grow or remain bounded. These simulations must account for the complex gravitational interactions between all objects in the system and the subtle cumulative effects of orbital resonances and secular perturbations. Now we float toward consideration of the relativistic effects that influence the dynamics of the Kepler-16 system. While the gravitational fields in this system are much weaker than those around compact objects, like neutron stars or black holes, the precision of modern astrometry and timing measurements is sufficient to detect subtle relativistic corrections to Newtonian orbital mechanics. The most significant relativistic effect in the Kepler-16 system is the relativistic advance of periastron, which causes the elliptical orbits of both the stellar binary and the planet to precess slightly more rapidly than predicted by pure Newtonian mechanics. This effect, first observed in the orbit of Mercury around the Sun arises from the curvature of spacetime around massive objects, as described by Einstein's theory of general relativity. In the quiet space of relativistic physics, the magnitude of these effects in the Kepler-16 system is extremely small, typically contributing corrections of only a few oxycons per century to orbital precession rates. However, the cumulative effect of these corrections over the multi-billion-year lifetime of the system could potentially influence the long-term stability and evolution of planetary orbits. The gravitational wave emission from the Kepler-16 binary system represents another subtle relativistic effect that influences the system's long-term evolution. As the two stars orbit each other, they create ripples in spacetime that carry away orbital energy, causing the stellar orbits to gradually decay over cosmic timescales. The rate of orbital decay due to gravitational wave emission is extremely slow for stellar binaries like Kepler-16, with orbital decay timescales measured in billions of years. However, this process will eventually cause the two stars to spiral closer together, potentially affecting the gravitational environment experienced by the planet, and leading to long-term changes in the stability of circumbinary orbits. Gently, we discover that the detection of gravitational waves from systems like Kepler-16 is currently beyond the sensitivity of existing gravitational wave detectors, which are optimized for much higher frequency signals from compact object mergers. Future space-based gravitational wave detectors, such as the proposed LISA mission, may eventually be sensitive enough to detect signals from galactic binary star systems. The magnetic field interactions in the Kepler-16 system add another layer of complexity to the physical environment. Both stars in the binary system likely possess magnetic fields generated by dynamo processes in their convective interiors, and these fields may interact with each other and with any magnetic field that might be generated by the planet. The stellar magnetic fields can influence the production and structure of stellar wind streams, of charged particles that flow outward from the stellar surfaces. In binary systems, these winds can interact in complex ways, creating shock fronts, magnetic reconnection events, and other high-energy phenomena that contribute to the overall electromagnetic environment of the system. Like whispers in the night, the interaction between stellar magnetic fields and stellar winds in the Kepler-16 system creates a dynamic electromagnetic environment that varies on multiple time scales. Short-term variations occur as the stars rotate on their axes, modulating the orientation and strength of their magnetic fields, while longer-term variations are driven by the orbital motion of the binary system, the planet Kepler-16b, if it possesses its own magnetic field, would interact with this complex electromagnetic environment in ways that could affect its atmospheric structure and evolution. Charged particles in the stellar winds could be channeled by the planet's magnetic field toward its polar regions, potentially creating auroral displays and driving atmospheric chemistry through particle bombardment. The hydrodynamic effects in the Kepler-16 system extend beyond simple gravitational dynamics to include the influence of stellar winds, radiation pressure, and potentially even material exchange between the components of the system. While these effects are generally much weaker than gravitational forces, they can accumulate over long time scales and influence the system's evolution. In the quiet space of fluid dynamics, the interaction between stellar winds from the two stars creates complex flow patterns. In the interstellar medium surrounding the binary system, these flows can affect the motion of small particles and dust grains in the system, potentially influencing the formation and evolution of any circumstellar or circumbinary debris disks. The radiation pressure from the combined stellar output of the binary system affects the motion of small particles and can contribute to the dispersal of circumstellar material. This effect is particularly important for understanding the evolution of protoplanetary disks around binary stars and the processes that lead to planet formation in such environments. The Poynting-Robertson effect, caused by the relativistic drag force experienced by small particles that absorb and re-emit stellar radiation, leads to the gradual orbital decay of dust particles in the system. This process helps to clear debris from the inner regions of planetary systems over cosmic timescales, contributing to the evolution of circumstellar environments. Gently, we discover that the combined effects of radiation pressure, stellar winds, and gravitational perturbations create a complex dynamical environment for small bodies in the Kepler-16 system. The survival of dust particles, asteroidal bodies, and other small objects depends on a delicate balance between these competing forces, with different outcomes depending on particle size, composition, and orbital location. The chaotic dynamics that can arise in three-body gravitational systems represent one of the most fascinating aspects of circumbinary planetary physics. While the Kepler-16 system appears to be dynamically stable over long time scales, small changes in initial conditions or system parameters could potentially lead to chaotic orbital evolution, where the future motion of objects becomes fundamentally unpredictable. The mathematical theory of chaos provides important insights into the boundary between stable and unstable motion in systems like Kepler-16. The existence of chaotic regions in phase space mathematical representations of all possible orbital configurations helps scientists understand why some circumbinary orbits are stable while others lead to planetary ejection or collision with the host stars. Like whispers in the night, the signatures of chaotic dynamics in astronomical systems can be detected through careful analysis of orbital timing variations and the statistical properties of planetary orbital elements. The absence of strong chaotic signatures in the Kepler-16 system provides evidence for its long-term dynamical stability. The concept of Hill stability provides a mathematical framework for understanding the conditions under which circumbinary planetary orbits remain stable over long time scales. Hill stability analysis determines the maximum distance from a planet at which test particles can maintain stable orbits, defining the effective gravitational sphere of influence of the planet. In the complex gravitational environment of a binary star system, the Hill stability regions around planets are smaller and more complex than in single star systems. This has important implications for the formation and retention of satellite systems around circumbinary planets, as it limits the range of orbital distances where stable moon orbits are possible. As our journey continues, we begin to appreciate the remarkable precision required to maintain stable planetary orbits. In the gravitationally complex environment of a binary star system, the existence of Kepler-16b demonstrates that nature is capable of creating and maintaining such delicate gravitational configurations over billions of years, opening new possibilities for planetary system architecture throughout our galaxy. Now we float toward one of the most profound questions raised by the discovery of Kepler-16b, the possibility of life existing in binary star systems, where the familiar concept of a single habitable zone gives way to complex, time-varying regions of potential habitability. In the quiet space of astrobiological contemplation, we explore how life might adapt to the unique environmental conditions created by binary starlight, and what this might mean for the prevalence of life throughout our galaxy. The traditional concept of a habitable zone, the region around a star, where liquid water can exist on a planetary surface, becomes significantly more complex in binary star systems. Instead of a simple circular or elliptical region around a single star, the habitable zone in a binary system forms a complex, time-varying pattern that depends on the orbital positions of both stars and their relative luminosities. Gently, we discover that for the Kepler-16 system, the combined habitable zone of the binary stars extends from approximately 0.9 to 1 point for astronomical units from the center of mass of the system. This places the habitable zone well inside the orbit of Kepler-16b, which orbits at an average distance of about 0.7 astronomical units, and experiences surface temperatures far too cold for liquid water. However, the concept of habitability in gas giant systems extends beyond the planetary surface to include the possibility of habitable moons, large satellites orbiting within the magnetosphere of a gas giant planet can experience tidal heating that provides an additional energy source beyond stellar radiation, potentially creating habitable conditions even at distances well beyond the traditional habitable zone. The moons of Jupiter and Saturn in our own solar system provide compelling examples of how tidal heating can create potentially habitable environments. Europa Enceladus and Titan all show evidence of subsurface liquid water oceans maintained by tidal heating from their parent planets despite orbiting well outside the solar habitable zone. Like whispers in the night, the possibility of similar processes operating on hypothetical moons of Kepler-16b opens intriguing astrobiological possibilities. A large moon orbiting the gas giant could experience sufficient tidal heating to maintain liquid water beneath an icy surface, creating a protected environment where life might develop and thrive. The complex radiation environment created by binary stars would present both challenges and opportunities for life. The varying stellar flux as the two stars orbit each other would create complex cycles of illumination and radiation exposure that differ significantly from the relatively stable conditions experienced by planets orbiting single stars. In the quiet space of evolutionary biology, such variable conditions might actually favor the development of more adaptable and resilient forms of life. Organisms that evolved under constantly changing stellar conditions might develop sophisticated mechanisms for dealing with environmental variability, potentially making them more robust than life forms that evolved under stable single-star conditions. The spectral characteristics of the Kepler-16 binary system would also influence any photosynthetic processes that might evolve on planets or moons in the system. Kepler-16a, being a K-type star, emits more red and infrared light relative to visible light compared to our Sun, while the smaller Kepler-16b contributes additional red and infrared radiation. Photosynthetic organisms that evolved in the Kepler-16 system would likely be adapted to efficiently capture and utilize red and near-infrared photons, potentially developing photosynthetic machinery that differs significantly from the chlorophyll-based systems that dominate Earth's biosphere. Such organisms might appear black or very dark red to human eyes, as they would absorb most visible light rather than reflecting green wavelengths. Gently, we discover that the seasonal variations caused by the elliptical orbit of a circumbinary planet would create additional complexity for any potential biosphere, unlike Earth's seasons, which are caused by axial tilt and create predictable annual cycles. The seasons on a circumbinary world would be driven by changing distance from the binary stars, and would follow the planet's orbital period rather than its rotation period. For Kepler-16b, with its 229-day orbital period, these seasons would be significantly shorter than Earth's annual cycle. However, the intensity of seasonal variations would be much greater due to the planet's elliptical orbit, with the amount of stellar radiation received varying by approximately 80% between closest and farthest approach to the binary stars. The atmospheric dynamics driven by these extreme seasonal variations would create complex weather patterns and climate zones that could influence the habitability of any moons orbiting the planet. Large-scale atmospheric circulation patterns might transport heat and moisture between different regions, potentially moderating the effects of seasonal variations in some areas, while amplifying them in others. Like whispers in the night, the magnetic field interactions in binary star systems could affect the habitability of orbiting planets and moons through their influence on atmospheric retention and the penetration of harmful stellar radiation. The complex electromagnetic environment created by two stellar magnetic fields might provide better protection from cosmic rays in some circumstances, while creating more intense particle bombardment in others. The aurora phenomena on planets and moons in binary star systems would likely be far more complex and spectacular than those observed on Earth. The varying stellar wind conditions and magnetic field orientations as the binary stars orbit each other would create constantly changing auroral displays that could play important roles in atmospheric chemistry and energy balance. From an astrobiological perspective, the question of whether life could originate in binary star systems is particularly intriguing. The complex environmental conditions might favor certain pathways to abiogenesis, while hindering others, potentially leading to the evolution of life forms with biochemistries and metabolisms quite different from those found on Earth. In the quiet space of prebiotic chemistry, the varying radiation environment in binary systems could drive novel chemical reactions and create complex organic molecules that might not form under the more stable conditions. Around single stars, the periodic changes in temperature, radiation flux, and atmospheric chemistry might provide the energy gradients and chemical diversity necessary for the emergence of self-replicating systems. The long-term stability of binary star systems also has important implications for biological evolution. While individual planets and moons might experience complex environmental variations on short time scales, the overall stability of the binary system over billions of years provides the long-term environmental persistence that appears necessary for the evolution of complex life. The discovery of multiple circumbinary planetary systems by the Kepler mission suggests that such systems are relatively common in our galaxy. If even a small fraction of these systems harbor habitable moons or planets, the potential sites for life in the galaxy could be significantly larger than estimates based solely on single-star systems. Gently, we discover that the search for biosignatures in circumbinary systems presents unique observational challenges. The complex lighting conditions and orbital dynamics make it difficult to obtain stable, long-term observations of atmospheric composition and other potential indicators of biological activity. Future space-based telescopes with advanced coronagraphic capabilities might be able to directly image large moons around circumbinary gas giants, potentially allowing for spectroscopic analysis of their atmospheres, the detection of oxygen, ozone, methane, or other potential biosignatures in such atmospheres would provide compelling evidence for biological processes operating in binary star systems. The SETI implications of circumbinary planets are also worth considering. If technological civilizations can arise on planets or moons in binary star systems, they would experience a very different relationship with their cosmic environment than civilizations arising around single stars. Their understanding of astronomy, physics, and cosmology might develop along different paths, potentially influencing their approaches to interstellar communication and exploration. Like whispers in the night, any radio signals or other technological signatures from civilizations in binary star systems might exhibit characteristic patterns related to the orbital dynamics of their home systems. The periodic changes in stellar interference and atmospheric conditions might create predictable variations in transmitted signals that could serve as identifying signatures for circumbinary civilizations. The philosophical implications of life in binary star systems are profound. The discovery that life can potentially arise and thrive in such gravitationally complex environments expands our conception of habitable worlds and reinforces the idea that life might be far more adaptable and widespread than previously imagined. The concept of planetary protection also takes on new dimensions when considering binary star systems. The complex orbital dynamics and environmental conditions in such systems might require new approaches to preventing contamination during robotic exploration missions, as traditional sterilization and quarantine protocols might not account for the unique challenges posed by circumbinary environments. In the quiet space of comparative astrobiology, the study of potential life in binary star systems helps us understand the fundamental requirements for habitability and the range of environmental conditions under which life might arise. By expanding our definition of habitable environments beyond the simple single-star paradigm, we develop a more nuanced understanding of life's potential distribution throughout the universe. The atmospheric escape processes that affect planets and moons in binary star systems could also influence long-term habitability. The complex radiation environment and varying stellar wind conditions might accelerate atmospheric loss from some worlds while providing protection for others, creating a diverse range of atmospheric evolution pathways that could affect the development and persistence of biospheres. The role of impact events in binary star systems adds another layer of complexity to astrobiological considerations. The gravitational perturbations from binary stars might influence the dynamics of asteroid and comet populations, potentially affecting the frequency and intensity of impacts on planets and moons in the system. Gently, we discover that while large impacts are generally considered detrimental to life, Small impacts might actually benefit biological evolution by creating periodic environmental stress that drives adaptation and speciation. The complex orbital dynamics in binary systems might create unique impact patterns that could influence evolutionary pathways in subtle but important ways. The potential for panspermia, the transfer of life between different worlds within a system, might also be enhanced in binary star systems. The gravitational perturbations could more easily eject material from planetary surfaces, potentially facilitating the transport of microorganisms between planets and moons within the system. The study of extremophile organisms on Earth provides important insights into the potential for life in the challenging environments of binary star systems. Organisms that thrive in conditions of extreme temperature variation, intense radiation, or unusual chemical environments demonstrate that life can adapt to far more diverse conditions than originally thought possible. As our journey continues, we begin to appreciate that the universe of potential habitable worlds is far richer and more diverse than early astrobiological studies suggested. The existence of stable planetary systems around binary stars effectively doubles the number of potential sites for life in our galaxy, opening vast new frontiers for astrobiological research and expanding our conception of life's cosmic possibilities. As our journey continues, we drift gently toward the future horizons of circumbinary planet research, where new generations of telescopes and observational techniques will deepen our understanding of worlds like Kepler-16b and reveal countless other binary planetary systems throughout our galaxy. In the quiet space of scientific anticipation, we contemplate the technological advances and mission concepts that will transform our knowledge of these exotic worlds in the years to come. The James Webb Space Telescope, with its unprecedented infrared sensitivity and high-resolution spectroscopic capabilities, represents a quantum leap forward in our ability to study circumbinary planetary systems. While JWST cannot detect the tiny transit signals of planets like Kepler-16b, it can provide detailed atmospheric characterization of larger, warmer circumbinary worlds through transmission and emission spectroscopy. Gently, we discover that JWST's ability to observe in the infrared portion of the electromagnetic spectrum is particularly valuable for studying circumbinary planets, which often orbit at relatively large distances from their host stars and emit most of their thermal radiation in infrared wavelengths. The telescope's exquisite sensitivity will allow astronomers to detect atmospheric constituents like water vapor, carbon dioxide, and methane in the atmospheres of these distant worlds. The upcoming Plato planetary transits and oscillations of stars mission, scheduled for launch in the late 2020s, will continue the legacy of Kepler by conducting high-precision photometric monitoring of bright stars. Plato's improved sensitivity and longer mission duration will enable the detection of smaller circumbinary planets and planets with longer orbital periods, expanding the census of known circumbinary worlds. The Roman Space Telescope, formerly known as WFIRST, will contribute to circumbinary planet science through its gravitational microlensing survey. This technique can detect planets by observing the gravitational lensing effects they create when they pass in front of background stars. Microlensing is particularly sensitive to planets at large orbital distances, complementing transit surveys that are most sensitive to close-in planets. Like whispers in the night, the gravitational microlensing signals from circumbinary planets create complex light curves that encode information about both the planetary and stellar components of the system. The Roman telescope's wide-field survey will monitor millions of stars simultaneously, potentially discovering hundreds of new circumbinary worlds and providing crucial statistics about their abundance and properties. Ground-based surveys using advanced adaptive optics systems are also contributing to our understanding of circumbinary systems. The direct imaging of circumbinary planets remains extremely challenging due to the brightness of the host stars, but improvements in coronagraphic techniques and the development of new observational strategies may eventually enable the direct detection and characterization of these worlds. In the quiet space of technological development, the next generation of extremely large telescopes, including the 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope will provide unprecedented angular resolution and light-gathering power for the study of binary star systems and their planetary companions. These giant ground-based telescopes, combined with advanced adaptive optics systems and sophisticated coronagraphic instruments, may be capable of directly imaging large circumbinary planets and even their major moons. Such observations would provide detailed information about atmospheric composition, weather patterns, and surface properties that cannot be obtained through transit observations alone. The development of space-based interferometry missions represents another exciting frontier for circumbinary planet research. Interferometric techniques can achieve extremely high angular resolution by combining light from multiple telescopes, potentially enabling the direct detection and characterization of Earth-sized planets in the habitable zones of nearby binary stars. Gently, we discover that the search for moons around circumbinary planets represents one of the most challenging but potentially rewarding areas of future research. The gravitational signatures of large moons would create subtle variations in planetary transit timing and duration that might be detectable with next-generation observational precision. The development of new data analysis techniques, including machine learning algorithms and advanced statistical methods, will play crucial roles in extracting the maximum scientific information from observations of circumbinary systems. These complex systems generate datasets with subtle signals and complex correlations that benefit from sophisticated analysis approaches. Theoretical advances in n-body dynamics and planetary formation theory will also contribute to our understanding of circumbinary worlds. High-resolution numerical simulations of planetary formation in binary star environments will help explain how planets like Kepler-16b form and survive in such gravitationally complex environments. Like whispers in the night, the long-term stability studies of circumbinary planetary systems require computational resources that were unavailable when Kepler-16b was first discovered. Modern supercomputers can integrate the equations of motion from millions of years of system evolution, providing insights into the long-term fate of these planetary systems. The study of circumbinary planet atmospheres will benefit enormously from advances in three-dimensional climate modeling. These models must account for the complex time-varying stellar irradiation patterns created by binary host stars, requiring sophisticated radiative transfer calculations and atmospheric dynamics simulations. The development of new observational techniques for detecting biosignatures in circumbinary planetary systems represents a particularly exciting area of future research. The complex lighting conditions and orbital dynamics in these systems require novel approaches to spectroscopic observations and the interpretation of atmospheric composition data. Let us drift into contemplation of the broader implications that future circumbinary planet discoveries will have for our understanding of planetary system formation and evolution. Each new detection adds to our statistical knowledge of these systems and helps constrain theoretical models of how planets form and survive in binary star environments. The frequency of circumbinary planets in our galaxy remains an open question that future surveys will help answer. Current estimates suggest that between 1% and 10% of close binary star systems might host detectable planets, but these estimates are based on small number statistics and may change significantly as more systems are discovered. In the quiet space of galactic astronomy, the abundance of circumbinary planets has important implications for our understanding of planetary system demographics and the potential prevalence of life in the universe. If circumbinary systems are common and can host habitable worlds, the number of potentially life-bearing planets in our galaxy could be much larger than current estimates suggest. The role of stellar evolution in circumbinary planetary systems will become increasingly important as these systems are studied over longer time scales. As binary stars evolve and change their luminosities, masses, and orbital properties, the habitable zones in their systems will shift, potentially affecting the long-term habitability of any planets or moons. The discovery of circumbinary planets around evolved stellar systems, including white dwarf binaries, neutron star binaries, and systems containing red giant stars will provide crucial insights into how planetary systems survive and evolve through dramatic phases of stellar evolution. Gently, we discover that the study of planet formation in binary star systems is advancing through a combination of observational discoveries and theoretical modeling. The presence of planets like Kepler-16b demonstrates that planet formation can occur in circumbinary disks, but the detailed mechanisms remain poorly understood and represent an active area of research. Future observations of protoplanetary disks around young binary stars will provide direct evidence for ongoing planet formation processes in these environments. The Atacama Large Millimeter Ray (ALMA) and other radio telescopes are already beginning to reveal the structure and dynamics of circumbinary disks, showing how material flows and accumulates in these complex gravitational environments. The development of new laboratory techniques for studying the physical and chemical processes relevant to circumbinary planet formation will complement observational and theoretical studies. High-pressure experiments, impact studies, and chemical reaction studies under exotic conditions will help constrain models of how planets form and evolve in binary star systems. Like whispers in the night, the interdisciplinary nature of circumbinary planet research brings together expertise from many different fields of astronomy and planetary science. The continued collaboration between observers, theorists, and laboratory scientists will be essential for advancing our understanding of these complex systems. The potential for citizen science contributions to circumbinary planet research should not be overlooked. Projects like Planet Hunters have already demonstrated the value of engaging amateur astronomers and the general public in the analysis of astronomical data, and similar approaches could be applied to the search for new circumbinary worlds. The educational and outreach opportunities presented by circumbinary planets are particularly valuable because these systems capture the public imagination while illustrating fundamental concepts in physics, astronomy, and planetary science. The science fiction appeal of Worlds with Two Suns provides a natural bridge between popular culture and rigorous scientific research. In the quiet space of scientific reflection, we recognize that the discovery of Kepler-16b represents just the beginning of our exploration of circumbinary planetary systems. Each new discovery builds upon previous knowledge while raising new questions and opening new avenues for investigation. The long-term vision for circumbinary planet research includes the eventual direct imaging and detailed characterization of these worlds, potentially including the detection of atmospheric biosignatures and the discovery of habitable moons. Such achievements would represent profound milestones in our understanding of life's potential distribution throughout the universe. The development of interstellar mission concepts for studying nearby circumbinary systems represents the ultimate extension of this research program. While such missions remain far in the future, the detailed study of systems like Kepler-16 provides the scientific foundation for planning eventual robotic exploration of these exotic worlds. Now we float toward our final contemplations of this remarkable planetary system and the broader implications of its discovery for our understanding of the cosmos. The story of Kepler-16b is ultimately a story about the incredible diversity and creativity of planetary system formation and the endless capacity of the universe to surprise and inspire us with its complexity and beauty. Gently, we discover that our journey through the science of Kepler-16b has taken us from the basic principles of stellar evolution and planetary formation to the cutting edge of exoplanet research and astrobiology. Along the way, we have encountered profound questions about the nature of planetary systems, the potential for life in the universe, and our place in the cosmic order. The existence of worlds like Kepler-16b reminds us that the universe is far stranger and more wonderful than our terrestrial experience might suggest. The cosmos is filled with planetary systems that operate according to physical principles we understand but produce outcomes that challenge our preconceptions and expand our sense of what is possible. Like whispers in the night, the faint signals from distant worlds carry messages across the vast emptiness of space, telling us stories of planets that dance around binary stars, of gravitational choreography that has continued for billions of years, and of the endless creativity of cosmic evolution. The discovery of Kepler-16b and other circumbinary planets has transformed our understanding of planetary system architecture and demonstrated that stable planetary orbits are possible in gravitational environments far more complex than our own solar system. This knowledge expands the range of conditions under which we might expect to find planets and, potentially, life in the quiet space of cosmic perspective. We recognize that each planetary system represents a unique experiment in gravitational physics, stellar evolution, and planetary formation. The diversity of outcomes from simple single-planet systems to complex multi-planet architectures, from single-star systems to circumbinary worlds reflects the rich interplay of physical processes that shape cosmic evolution. The study of Kepler-16b has also highlighted the importance of precision measurements and sophisticated theoretical modeling in modern astronomy. The detection and characterization of this world required the coordinated application of space-based photometry, advanced data analysis techniques, and complex n-body gravitational simulations. The collaborative nature of modern astronomical research exemplified by the large international teams that work on missions like Kepler and the theoretical groups that develop models of planetary system dynamics demonstrates the power of coordinated scientific inquiry to tackle the most challenging problems. In our understanding of the cosmos, gently, we discover that the story of Kepler-16b is still being written as new observational capabilities come online and theoretical understanding continues to advance. Our knowledge of this remarkable world and others like it will continue to grow and evolve. Future discoveries may reveal additional planets in the Kepler-16 system, moons orbiting the known planet, or other unexpected phenomena that will further enrich our understanding of circumbinary planetary systems. Each new piece of information adds to the complex picture of how these systems form, evolve, and potentially host life. The broader implications of circumbinary planet research extend beyond astronomy to touch on fundamental questions about the nature of complexity, the prevalence of life in the universe, and humanity's relationship with the cosmos. These worlds remind us that we live in a universe of extraordinary richness and diversity, where nature routinely produces outcomes that surpass our imagination. Like whispers in the night, the ongoing study of worlds like Kepler-16b continues to reveal new aspects of cosmic evolution and planetary system formation. Each observation, each theoretical advance, each new discovery adds another verse to the cosmic poem that describes the universe's endless capacity for creating beauty, complexity, and wonder. As we conclude our gentle journey through the science of Kepler-16b, we carry with us a renewed appreciation for the incredible diversity of planetary worlds and the remarkable achievements of human ingenuity that make their discovery possible. The universe is vast and full of wonders, and we have only begun to explore its infinite possibilities. In the quiet space of peaceful reflection, we recognize that our exploration of distant worlds is ultimately an exploration of ourselves and our place in the cosmic order. Each new discovery expands our perspective, challenges our assumptions, and reminds us of the profound connections that link us to the stars and planets that populate the infinite darkness of space. The gentle light of binary stars traveling across 245 light-years of empty space to reach our telescopes carries with it the story of worlds beyond our imagination, worlds where two suns rise and set, in alien skies where gravitational forces create complex orbital dances, and where the possibilities for life and complexity extend far beyond the familiar boundaries of our solar system. Gently, we discover that our cosmic journey continues, carried forward by human curiosity, scientific rigor, and the endless quest to understand our place in the vast cosmic ocean. The stars await our continued exploration, and countless worlds like Kepler-16b drift silently through space, waiting to reveal their secrets to future generations of cosmic explorers. And so we drift peacefully back to our own small world, enriched by our contemplation of distant suns and exotic planets, carrying with us the knowledge that the universe is filled with wonders beyond our wildest dreams. The cosmos is our home, and we are privileged to be conscious participants in its ongoing story of evolution, discovery, and endless possibility. Like whispers in the night, The universe continues its ancient conversation with those who listen carefully to its subtle signals. Through patient observation, rigorous analysis, and thoughtful contemplation, we participate in this cosmic dialogue, adding our own small voices to the eternal song of scientific discovery and human understanding. In the end, the story of Kepler-16b is our story to a tale of discovery, wonder, and the endless human quest to understand our place in the infinite cosmos. As we continue our exploration of the universe, we carry with us the knowledge that we are part of something far greater than ourselves, citizens of a cosmic community that extends across space and time to embrace all the worlds that orbit all the stars in all the galaxies of the observable universe. In the quiet space of final contemplation, we rest peacefully in the knowledge that the universe is both vast beyond comprehension and intimately connected to our daily lives. The same physical laws that govern the orbital dance of Kepler-16b also guide the motion of our own planet around the Sun, linking us across the light years to distant worlds and alien skies. And with this thought, our gentle journey through the cosmos comes to its peaceful conclusion, leaving us with a renewed sense of wonder, gratitude, and connection to the infinite universe that surrounds us. The stars continue their eternal dance, the planets follow their ancient orbits, and the cosmic story continues to unfold in ways both beautiful and profound. Good night from the sleepy scientist, and may your dreams be filled with the gentle light of binary stars and the quiet wonder of worlds beyond imagination.